Hi, everyone. Really excited to be here. Thank you all for the invitation. I am Rasheed, and the title of my presentation is Blind Magmatism, Abets Nonvolcanic Continental Rifting. This is work that was done in collaboration with Fola, you all know Fola, and William Menke at Columbia. So just before I go into the talk, I just want to briefly talk about myself and introduce myself to the rifting community. So I'm currently a geophysics postdoc at Columbia. Um, I mainly conduct reproducible research in geophysics. So everything I present today can be reproduced if you have the patience to go through my publication and actually look through the electronic supplements. My research is interdisciplinary. I mainly use geophysics and simple numerical modeling to address varying geologic problems. I've worked in Africa, in the Burma, Southern California, and now, East African Rift System. I've also been involved in, field deployments campaigns in the past. The picture on the lower right is me in Myanmar when I was deploying broadband seismographs. And I'm open to, invited talks, seminars, and future collaborations with anyone really on this call. All right, so here's the outline for today's talk. So, I'll go over the background, kind of the science question, and then I'll introduce the study area, which is the East African Rift System. I'll briefly go over some previous studies, and observations that are key to the current work that I'm presenting. And then we'll go over the data and methods used in the study, and then the results, and finally we'll have the conclusion and then questions, I guess, at the end. All right, so here's to the left is a schematic of the life cycle of a continental rift from initiation all the way to breakup and where you have rifted margins. The evolution of continental rifts, and this is a successful rift, which means that you had breakup eventually. The evolution of continental rifts is controlled by several competing geologic and geodynamic factors. Specifically for magma pore rifting, inherited structures are known to be critical for rift nucleation. So in the middle figure is showing an example of, foliations and then a fault plane, basically showing faults exploiting pre-rift basement structure in a rift system. And then on the right is, some driving forces that you normally see in extensional settings, along with various strengthening and weakening processes that you'd observe. And these are all figures from, the review paper published in Nature last year by Bruin. I recommend the paper to everyone. So, however, following the establishment of a rift basin, in magma pore rifts, we know that the role of inheritance is usually limited. And geodynamic models usually indicates that thermal weakening, which is usually in the form of magmatism, is essential for that continuous progressive rifting that you need in order to get to breakup. So, do rifts that lack volcanism, do they lack this thermal mechanical weakening process? That's, it's one of the questions we're trying to address. So kind of to recap, this is the science question is, what thermomechanical processes drive progressive weakening along magma pore rifts? To address that question, our study area is going to be the East African Rift System. And the approach is going to be seismology and some simple numerical modeling. Okay, so I have a lot of figures here. The first figure on the left is a map showing the East African Rift System. It's a classic example of continental rifting, and it's one of the largest active continental rift system on Earth. There are mainly two branches, right? The eastern branch is known as the magma ridge, and the western branch is known as the magma pore. And you can see, or you could observe that by looking at the triangles, which represents surface volcanism or volcanic centers. The map in the middle is sort of a geologic tectonic map showing how rifts essentially exploit pre-existing weaknesses during their formation. A dominant hypothesis why you have the two main branches is, you have hot material essentially rising from the African superbloom, essentially being deflected by the deeply rooted Tanzania craton, which made the eastern branch essentially rich in magma and leaving the western branch magma starved. Our study area is going to be the Tanganyika-Rukwa, which is shown by the black box over here. And as you can see, there's no evidence of surface volcanism in the area. So it's essentially non-volcanic rifts. So now let's look at some previous studies. So, some of the earlier imaging work, this is from a technique known as seismic tomography, and they're using surface waves. Essentially, surface waves travel along the surface of the Earth. This map is a map of the East African rift system, and the triangles are essentially seismographs that record the seismic waves from earthquakes. So this map's shown on the right, they're essentially depth slices of shear wave velocities, or known as S-wave velocities. The warmer colors essentially represents slow wave speeds, and the higher colors, or the blue colors or cooler colors, represents faster wave speed. So usually we interpret the wave speed as a proxy for temperature. So whenever you have a low shear wave velocity, usually means that you have a high temperature, and vice versa. So I highlighted the study area by this red polygon in the first depth slice. And what you've noticed is that the velocities are essentially faster than average, which implies that the subsurface structure is actually cold. And just to point out something, this was a study published in 2013. So it's not earliest, but it's one of the earlier studies, when we didn't really have as much data. And so if you take a look at a study like this, you would think that, in the western branch, especially in non-volcanic rift segments like, the red dash box area, which is Tanganyika-Rukwa, that there's really no subsurface magmatic influence. And this might just have been a resolution issue, really. So, moving forward, back in 2014 through 2015, the Tanga 14 array was deployed. It comprises 13 broadband seismic stations deployed on the Ufipo Ors between Lake Tanganyika and Lake Rukwa. It's the map on the right, on the left, shows the seismic stations as the purple triangles. On the right is a study that used the triangles on the stations essentially to build a local earthquake catalog. So, following the deployment and collection of this data, there's been, lots of new studies coming out from this non-volcanic rifts. And I also used some of this data in my current study. So here's an example of a previous study that utilized some of that data. This is a map showing, the diamond essentially represents crustal thickness and a parameter known as VPVS ratio. VPVS ratio is essentially the ratio of your P wave speeds to your S wave speeds. In this case, the technique used is known as receiver function. It's very similar to reflection seismology in the oil and gas industry, commonly used in exploration, for example. But instead, you're looking at converted waves rather than reflected waves. One thing to point out in this study is that these are crustal average results. So you're looking at everything from the mohole all the way to the surface. It's like an average of all of that. The key points here, they found really anomalously high VPVS ratios, similar to values you'd find in the more mature segments of the East African rift system. where you do have surface volcanism. And that indicated the presence of subsurface melts. But the problem with receiver functions, it doesn't tell you at what depth the melt really is because it's all crustal average. Also, in this study, they never really looked into the implication of that for progressive rifting in the area. This is a different study that looked at, again, using the same stations, looked at mantle anisotropy. They use a technique known as shear wave splitting. It's really common in seismology for looking at seismic anisotropy. So anisotropy is whenever you have some material symmetry. So seismic anisotropy just means that you're going to have your seismic wave speeds traveling faster in one direction versus another. And it usually indicates rock fabric. So things like aligned minerals, for example, will be in the mantle, or you can have cracks in the shallow crust filled with fluid, faults, fabrics, and even aligned melts in the crust can give you very strong anisotropic signals. So usually it's represented by the direction of the fast orientation of your polarization direction of the fast shear wave. And then usually they would, scale the size of the sticks by the strength of the anisotropic signal. So for example, like this, the shorter sticks would be the weaker anisotropic signals, and then they're oriented according to the polarization direction of the faster shear wave. So, we looked at surface observations, so subsurface observations in the area. So lines A to A prime and B to B prime, essentially seismic profiles, reflection profiles, interpreted in the area, basically showing that we're having strain localization along the intra-rift faults. And you can see a lot of seismicity as well. So we're getting increasing strain along the rift axis. So keep that in mind. So for our study, we decided to look, so we have, all of these different results. We have receiver functions showing high VPVS ratio, but it doesn't really give you the depth resolution. So we decided to look at crustal anisotropy. It's not very popular in the seismic community because it's using local earthquake data, which is really noisy. But if you're really patient and if you can look through the data manually, you can get some really clean results. So again, we're using the local earthquakes recorded by Tango 14, focused entirely in the crust. And this is kind of, a summary of our results. So again, the sticks represent the orientation of the fast polarization direction of the faster shear waves. And then in this case, we're color coding them by the strengths rather than, scaling the length of the sticks. And all of the polar plots essentially represent orientations for faults in the area, metamorphic fabrics. This is a summary of the mantle shear wave splitting result that I showed in the previous slides, and these are mega fractures. And below are the shear wave, crustal shear wave anisotropic results that we have. And then at the bottom is kind of a polar plot showing the result as a function of the event's depth and also colored by the crustal shear wave anisotropy. The takeaway point is that we're seeing that the crustal anisotropic strength is strongest for low crustal earthquakes with ray paths that are essentially sampling beneath the region of the crust with high VPVS ratio, which essentially provides a stronger evidence for low volume blind melts in the lower crust beneath the study area. Okay, now let's take a little step backwards and just zoom out a little bit, look at the topography. So when you zoom out a little bit from the study area, north and south, there are elevation anomalies that we see, and also in the study area. North and south, we already have surface volcanism. However, in the study area, there's no volcanism at the surface. In the past, structural geologists, especially Morley, has tried to explain the anomalous topography by looking at flexural uplifts on normal faulting. However, there's still discrepancies of up to 1 kilometer. And also we see high surface heat flow in the area and other subsurface, high subsurface temperature indicators like, your thermal springs, you have helium degassing as well. So using the range of surface heat flow measurements in the area, we essentially ran a very simple numerical model to look at the essentially the evolution of the isotherm in the region and look at the effect that it has on lithospheric strength, and also looking at thermal factors that can account for the elevation discrepancy, which is essentially what is shown here. So, at conditions where you have, high surface heat flow, the geothermal model essentially predict that you can have melt in those instances. And looking at thermal isostasy or the densification as a result of, partial melting in the lower crust can actually create some kind of anomalies that can lead to uplifts with, magnitudes that can explain the discrepancies in essentially the plateau that has not been explained previously. So this is just kind of, a conclusion, it's like the absence of surface volcanism does not necessarily imply the lack of magmatic support. We believe that the low crustal blind magmatism, even though it's low volume, is assisting non-volcanic continental rifting. And also this is relevant for climate change because we know volatile degassing can occur, for thousands of years before you actually have eruption. So that's all I have today. Thank you.
Thank you, Rasheed. That was great. Beautiful visuals. If anybody has any questions, they could put their hands up. I have one question with your crustal anisotropy. I was looking at values of like the blues are all like 0 to 0.5% anisotropy. Right. And you're saying the data is really noisy because it's all local earthquakes. How confident are you that you're actually picking up a shear wave split?
Oh, yeah. So this is an example of, it was really difficult, but everything was manual. Nothing was automated. So, from the picking of the shear waves to, looking at the manually checking, quality checking the results. So this is an example of shear wave splitting results, and it's usually very clean. So I have a very high confidence in the results.
Okay.
As far as the strength of the anisotropy, I feel like it also depends on the sort of velocity model you're using, which is not very accurate in the area. But relatively, I think areas where it's showing, stronger anisotropy, I think are indeed stronger. And then areas where it's weaker, I think they're indeed weaker, although there might be some error bars on the absolute values of the strength of anisotropic signals themselves. But relatively, I think it's accurate.